Hey everybody, just wanted to meet with you real quick and talk about your electric field activity that you're going to be doing this week. This is similar to an activity we usually do in lab where we set up a sheet of paper that has some silver paint on it, and then we set up a potential difference between the positive and negative terminals, and then you measure the potential field and the electric field. Because we're doing this at home, we're going to have you do this computationally by basically summing up the contributions due to a bunch of point charges on a line of charge, and from that computing the potential and electric field. So what you're going to do for this is you're going to be using Excel, and you're going to be calculating the force between two charges, the electric field magnitude between two charges, and the potential difference between those two locations. And so the background has the equations you're going to be using for this, and your setup for your Excel spreadsheet is described in here. So what you're going to wind up doing is building a map of the electric field and potential for a given distribution of charge. So let's take a look at that map first. That map looks like this, where you have a line of charge, those are the blue dots, and then everywhere you have an X, you're going to be measuring the electric field and the potential at those points. So in order to do that, what you're going to do is you're going to, from a given point, you're going to add up the contribution of each one of these point charges. And because we can sum those all together, you're going to wind up getting the total contribution from the entire line of charge. And you're going to be able to do that at these different points and draw a map of what the potential and electric field look like. So the way you're going to do that is you're going to set up an Excel spreadsheet. And that Excel spreadsheet is going to have the position where you're going to be doing the test. So it's going to be some X and Y along those X marks. And then you're going to have your line of charge. So you'll notice that the X values for this line of charge are all 0, and the Y values go from negative 0.1 to 0.1. So in order to calculate those, the first thing you need to know is how far apart they are. So this distance calculation here, let me go ahead and open up Excel real quick, and we'll do the first couple of these calculations together so you can see what that looks like. So here's my Excel worksheet, and let me just zoom in a little bit so you can see this. Whoops. Cancel that. There we go. Well, we'll just zoom in here. Okay. So the first thing you're going to do is you're going to choose your X0 point and your Y0 point. So these are going to be the points where you're doing the calculation. So let's say, for the sake of argument, we'll do this on the X-axis, so 0.0. So on the X-axis would be Y of 0.0, and then we'll do it at some point on the X-axis, 0.5, let's say. I think that looks good for, yeah, that's what you're doing over there. And then you're going to have your line of charge. Your line of charge is going to have the X and Y components. Those X components are going to be 0. Okay, so just for demonstration purposes, I'll make this not too long. And then your Y values are going to go from 0.1 down to some value. So I'm going to go ahead and put this 0.09. And once I have two of those like that, I can just drag that down. And again, we're going to just make this short for the sake of argument. So now what you're going to do is you're going to figure out the force, the electric field magnitude, and the potential difference between these two coordinates here and these two coordinates here. So the first thing I'm going to want to know to do that is the distance between them. So to get the distance between them, I'm just going to say, well, that's the square root of the difference between my X positions. So let's start with this one, and I'm going to want this to be stay that cell B1 right there. So I'm going to put those dollar signs there to make sure that stays that way. And then I want it to reference my X equals 0. So that's going to be the square root, square root of that So that's my x component. That's got to be squared. And then I'm going to add to that the difference between the y components, which is going to be this one. Again, I'm going to keep that fixed. I'm going to put those there. And then I'm going to subtract off this y component there. And that's going to change every time. And then that has to be squared again. Okay, so this is, if you look at this, this is the square root of the square of the difference in x, the square of the difference in y. That's going to give me the distance. Okay, and if we just look at that, that seems to make sense because we have a small change in y, small change in x. So that's going to be the distance here. And then to get this to propagate through my whole table, I just double click on the little corner here. Boom. Okay. So that gives me the distance between the x and y position in this map. If I go here, so I had chosen 0.5 and 0. So that's the difference between that point, this point, on and on and on. Okay. Then what I want to do is calculate the force. So the force, this is going to be the magnitude of the force. Well, I have that equation up here, right? The force is just the sum of the charge, or the product of the charges multiplied by a constant divided by the distance squared. Now we're going to assume, let's see, I think we assume that each of these charges would be 1 nanocoulomb by nanocoulomb squared. Okay, so that's two charges, each a nanocoulomb, and then I'm going to divide that by the distance squared. And that's going to give me some force. And if you want to double check that, if you come up here, should get something like 10 to the minus 8. Okay. And then I'm going to do the magnitude of the electric field, but the magnitude of the electric field is just the magnitude of the force divided by one of the charges, right, our test charge. So we're going to say 1 e to the minus 9. So that should be something like 34. That looks pretty good. And then finally, the potential difference is this magnitude of the electric field times the distance. So I'm going to go ahead and put in potential here. And I'm going to say that's equal to the distance times that. All right. So got my magnitude of the force, magnitude of the electric field, magnitude of the potential. Take all those and let's do that. So what this is showing here is now this is the potential due to a single point charge at 0.1 measured at 0.5 and 0. And same thing with this at a position of a point charge of 0.09 measured from this position, and so on. So the sum of these potentials is going to be the total potential at this point. Now, the forces and the electric field magnitude and the force magnitudes, you can't sum those up to get the actual electric field and force at those points because those are vectors and we have to worry about direction. But with potentials, I can just add those up. So I'm just going to sum these finally and get my result. Okay, and if you go down and look at your dealio here, would be like summing all of those together. So that's basically giving you the potential difference at those points. Now, this is the number you want. So this is the number you're going to map. But let's see what happens when I change these positions. So we expect if I change this to say 0.8, the potential difference to go down, right? Because I'm at a further point now, so I basically have a lower potential energy. And if I make this closer, I expect it to go up. Right? So you're going to make a map of that, and you're going to use this spreadsheet every single time to make a map of your electric potentials. All right, so I hope that gives you a good start, and if not, I'll be in my office hours this morning, and you're welcome to join me and talk about it.